You know what? I didn't start recording. Okay. Guys, I'm just going to do a quick recap of the thing. So we are 8 minutes into class. If you are watching this in the future, you have missed the first 8 minutes. I'm going to give a quick recap of the things I said in the first 8 minutes, and hopefully catch everything. The record button. So we're talking about extrema. Extrema just means maxes and mins. We talk about local maxes and mins, and we talk about absolute maxes and mins. So local extrema, absolute extrema. Local is just going to be you can have multiple local mins, local maxes. So anything that's the top of a hill is going to be a local max. Anything that's the bottom of a valley is going to be a local min. You can have multiple on a graph. However, there's also this idea of absolute extrema. So you can have one point on the graph that has the absolute highest y value. So on this graph right here, this is an absolute max because for this entire graph, this is the highest y value. This graph does not have an absolute max or an absolute min because it goes off in both directions. So these y values will get smaller and smaller. These ones will get bigger and bigger. There's no absolute max or min. Over here on this picture, color that in purple. The absolute max of this picture, right up here, absolute min is way down here. So the highest y value, lowest y value. Along with having absolute maxes and mins, both of these pictures also have local maxes and mins. So there's a local min here, a local max here, local min here, local max here. There's a debatable area whether or not endpoints can be local maxes or mins. In our case, we're not going to consider them maxes or mins because we're not going to consider them local maxes or mins because we're defining local maxes and mins to be on an open interval. So that is my quick recap, my 2-minute recap of things that I've said. So now you learn this material in Math 126, and we're going to relearn it in a new way, in a calculus way. So we're going to talk about two things. We're going to talk about critical values. We're going to talk about important values. So here's a pseudo definition of an important value. A function f has an important value, and we're going to call those IVs, at an x value if the derivative is 0 at that x value, or if the derivative doesn't exist. The actual definition, which we're going to write down here, adds one more stipulation to this definition. So for the definition of critical values, it has like an additional stipulation. So there's critical values and important values. Important values, the derivative is 0 at that point or does not exist. For a critical value, which we are going to call CV, critical value CV, you're going to be a critical value if, here's the additional stipulation, I'll underline it in purple, f of a exists, and we have that either these guys right here, the derivative is 0 or the derivative doesn't exist. All right, so here's the difference between a critical value and an important value. The only difference is that critical values require that the x value is in the original domain of the function. So all critical values are important values, but not all important values are critical values. So an important value has either f prime of a, this is a critical value at x equals a, f prime of A equals 0, or f prime of A dne. A critical value has the same stipulation because it is an important value, and x equals A is in the domain of f. i.e., f of A exists. So f of A can only exist if x equals A is in the domain of the original function. So critical values just have one additional requirement. Now here's the reasoning behind why we're defining these things. Maxes and mins can only happen at critical values. Maxes and mins can only happen at critical values, because think of what it looks like. And when I say maxes and mins, local maxes and mins can only happen at critical values. Why that is because look at these places where you have maxes or mins. The tangent line in those places is horizontal. That's the only place you're going to have a local max or min, is if the tangent line is horizontal, i.e. the slope is 0, or in the fun case that you have like a nice zigzaggy graph. Here's a max, here's a local max, here's a local min, here's a local max. In this case, the derivative doesn't exist because it's a corner. So the only possible place where there could be a max or a min is either they have a horizontal tangent line, or it has no tangent line because it's at a peak. So we can find critical values and important values. You find important values first, then you cancel out all the ones that aren't in the domain so that you only have critical values. And from there, you're able to determine the local maxes and mins. So let's start with just finding important values and critical values. All right, so here we have example 3.1.1. Find all important and critical values of f of x equals 1/4 x to the 4th minus x cubed minus 2x squared plus 12x plus 7. Your first step is to find the derivative. So the derivative here, 1/4 times 4 is 1, so this will just be x cubed minus 3x squared minus 4x plus 12. Then, for finding critical values, or for finding important values, you set it equal to 0, or find out where it doesn't exist. But because this derivative is a polynomial, there's no domain issues. The original is a polynomial. This is a polynomial. So there's no domain issues. You're not going to have f prime of A not existing. Additionally, there's no domain issues. So all important values are going to be critical values because all of the x values are in the domain. So this means all important values are critical values because the domain is negative infinity to infinity because it's a polynomial. So your next step is finding where f prime is either 0 or undefined. Once again, there's no place where this doesn't exist, so we're just going to set it equal to 0. You're going to find that a lot of your problems in calculus from here on out are solved by finding a derivative and setting it equal to 0. That's really just going to become a thing you do regularly. And you're going to come to the point where it's, I don't know what to do. I think I'll take a derivative and set it equal to 0. That's the point it's going to come to. Is that always the answer? No. Is it the answer enough of the time? Yes. So take a derivative, set it equal to 0. This is going to require factoring. So I'm going to do factoring by grouping. For the first group, because we have two groups here, I can factor out an x squared, and I get x minus 3. For the second group, I can factor out a negative 4, and I'm also left with x minus 3. I can pull an x minus 3 out, and then I have x squared minus 4. And I can factor x squared minus 4 into x plus 2 times x minus 2. So the important values are going to be all the answers you get down here. So by setting each of these factors equal to 0. So you're going to get x equals 3, negative 2, positive 2. Those are the important values. Now, because all of these x values, normally at this point what you do is you check to make sure all of these x values work in the original. But the original, once again, is a polynomial, so all of these ones will work in here. So all of those important values are critical values. So that's one example of finding important values and critical values. For this next example, we're given a function g of t, and we're also given the derivative. All right, so the author of the notes has already taken the derivative for us. We don't have to take the derivative. We're just asked to find the important and critical values of the function. So this part where we find the derivative is already done. To find the important values, we want to look to find out where this is either equal to 0 or undefined. What's important here? It's equal to 0 if the numerator equals 0. Right? That's when the derivative will be equal to 0. This is important. The only time a fraction can be 0 is if the numerator and the numerator alone is 0. G prime of t is not going to exist when the denominator equals 0. So we're going to find the x values where the numerator is 0, and the x values, or the t values rather, the t values when the numerator is 0 and the t values when the denominator is 0. And those are going to be our important values. It's really important that we find these important values, not just critical values. Critical values are going to have a lot of importance, but important values are going to be important. That's why they're called important values. They're going to be important because things happen at important values. Even if you can't have a max or a min at an important value, you can still have some interesting things happen. So it's important to be able to find them. So we'll start off with g prime of t equal to 0. So we'll start off with finding out where the derivative is 0. So we're letting the numerator equal 0. You can include the negative or not. It's not going to matter. So I have 2 times 2t plus 7 times t plus 1 equal to 0. This 2 out here doesn't do anything for you, so I can ignore it. This gives me t equal to negative 7 halves, and this one will give me t equal to negative 1. So if I'm writing down my list of IVs, I have -7/2, I have -1, and then I'm looking for where g prime of t is non-existent. So I'm setting the denominator equal to 0. Here I'm getting -2 and 4. So those are my important values, the places where the numerator is 0, the places where the denominator is 0. For my critical values, I'm going to look for domain issues in the original function, and I'm going to take them out. So this is the original function right here. And the domain issues it's going to have is the denominator can't be equal to 0. This can be factored into t minus 4 times t plus 2, not equal to 0. So t cannot be equal to 4, and t cannot be equal to -2. 4 and -2 are not in the domain of G. So they can't be critical values. So every other point in here except for 4 and -2, those ones are important values. So -7/2 and -1. At this point in time, you might say to yourself, well, it just looks like the places where g prime of t does not exist are the places where like those are going to be important values but not critical values. And that is sometimes true, and that is sometimes not true. So it's not a rule we can use because it's not always true. Sometimes it is, sometimes it's not. You always have to double check them in the original function to see if they're in the domain or not. Can I answer any questions on this one? Okay. If you have questions, feel free to shout them out. All right, so a new theorem, which I've already kind of alluded to. If you have a relative extrema that at x equals a, then x equals a is a critical value of f. This is something I talked about way up here. I said these critical values are important because if you have a tangent line whose slope is 0, or you have a tangent line that doesn't exist, like the slope that doesn't exist, if the derivative doesn't exist there, those are the places where extrema can occur. Now, what's not true, it's not true that you'll always have a max or a min, a local max or min, if you have a critical value. Not all critical values give you extrema. So if I kind of do like a bubble chart here, like, so you have this, and this are like all your IVs, your important values. Now, some, but not all, of your IVs are critical values. Now, some, but not all, of your critical values are extrema. Right? All extrema are critical values. All extrema are important values. All critical values are important values. But there's some exclusions in here. You can have critical values that are not extrema. You can have important values that are not critical values. So this is saying the reverse direction is not necessarily true. So not all critical values are extrema. So let's do some more finding of critical values. So find the critical values of this function right here. G of x equals x squared e to the 3x minus 7. Your first step is taking the derivative. This is going to be a product rule, right? F, G. So G prime of x is equal to F prime is 2x, G is e to the 3x, plus G prime is 3 e to the 3x, F is x squared. I'm going to rewrite this as 2x e to the 3x plus 3x squared e to the 3x. Then you're going to do two things. You're going to look for where the derivative is 0 and where the derivative doesn't exist. So g prime of x equals 0. So we take the derivative, 2x e to the 3x plus 3x squared e to the 3x, and we set it equal to 0. You are going to need a factor here. It looks like I can factor out an x, and I can factor out an e to the 3x, leaving me with 2 plus 3x equal to 0. So I'm factoring out an x, and I'm factoring out an e to the 3x. There's 3 different pieces here to set equal to 0. So if you set x equal to 0, you get x equal to 0. If you set e to the 3x equal to 0, you're not going to get any answers. So normally the way that you would solve a problem like this, you would take the natural log of both sides. But let me tell you, when you do that, the ln and the e cancel, so you get 3x equals ln 0. But ln 0 doesn't exist. So you don't get any zeros from this guy right here. E to the 3x will never equal 0. And then you can set 2 plus 3x equal to 0. You're going to get x equal to negative 2/3. So these are the 2 important values I've found. I found 0 and I found negative 2/3. I'm also going to look for places where the derivative doesn't exist. So you're looking for denominators equaling 0. You're looking for negatives under the square root, but there's no problems here. That there's no denominators to worry about. There's no inside of ln. There's no square roots. So this is nowhere. So those are all the important values, and now we want to limit them to just the critical values. To do that, we're just looking to see if there are any domain issues in the original function. And there's not. So all of your important values are critical values because there's no domain issues. Can I answer any questions there? I'm going to pull up some practice problems. So Unit 3 does not have any exercises in it yet, so I'm going to have to post exercises separately. That'll be done soon. I figure nobody's going to be working on that. I think everyone's working on the test this week, but I'll make sure to get some homework problems up soon. I'm going to put down some. We'll come to back to this example, but I'm going to give you guys some to try. Finding the important values and critical values. So let's see. I'm looking at this. I'm hoping none of these are going to be too bad. Let's do f of x equals 2x cubed plus x squared plus 2x. And let's do g of x equals x to the 1/3 Is this really the one I want to do? No, actually, I changed my mind. Yeah, let's do this. So go ahead and find the important values and critical values for these ones. Take the derivative, set it equal to 0, find where it's undefined, find where it's equal to 0, and then filter out the critical values from the important values. I'm going to go ahead and give you 5 minutes just because this is a new one. And I forgot to push record again. So people watching this, part A doesn't work out. My bad. We're working on part B now. We've taken the derivative, we've rewritten it. Someone has to catch me on this recording. What a day. So sorry you missed the first bit. We had to recap. Sorry for people watching this in the future. Part A doesn't work out. Part B is what we are working on right now. We have taken the derivative. We did some chain rule. We are now simplifying it. These 2's are going to cancel. So this minus, I'm going to come out here. This minus, a plus a negative, is just a minus sign. T squared over 4 minus t square root of 4 minus t squared. Now, we have to set this thing equal to 0 and solve. This is really, really where it's important to remember, embrace, and love your algebra, right? What do we do here? We need to make a common denominator. Right? There's multiple ways of doing this. The way that I'm going to suggest here, you're going to make a common denominator. The denominator that we want is the square root of 4 minus t squared. So to do that, you are multiplying by the square root of 4 minus t squared on the top and bottom. And we can leave the other one alone because he already has that. Okay. Now, beautiful, beautiful thing happens in this problem. These square roots are going to go ahead and cancel out, right? It's the same thing under the square root. So the square roots will cancel out. And you'll just have 4 minus t squared over square root 4 minus t squared minus t squared over square root 4 minus t squared. equal to 0. Now that they both have the same denominator, we can combine together the numerators. So we have 4 minus t squared over the square root of 4 minus t squared equal to 0. Combine together like terms on the top, so 4 minus 2t squared over square root of 4 minus t squared equal to 0. Why don't we do a little bit of this, a little bit of rearranging. So really there's two things we can do at this moment. We're setting it equal to 0 because we want to find out where the numerator equals 0 and where the denominator equals 0. Because remember, for our important values, we need where it's equal to 0, where the derivative is equal to 0, and where the derivative doesn't exist. So for where this derivative is equal to 0, it's where the numerator equals 0. You can factor out a 2. And then you could factor this with difference of squares. Really, I mean, you're going to get 2 minus t squared equals 0. You're going to get t squared equal to 2. The important thing here is that when you do the square root property, because you're going to take the square root of both sides, that you put a plus or minus on here. So you get t equals plus or minus the square root of 2. And that is for the top. For the bottom, now really, there's whole intervals where this entire function doesn't exist. We're just going to kind of look at the places where it's going to have, where it's going to be 0. Let's just look at those issues. The reason we're not going to concern ourselves so much with the other intervals where it doesn't exist is because those are going to be issues in the original function as well, which we'll come back to. These ended up not being great problems, which is a little disappointing to me. Oh well. So looking at where the denominator is equal to 0, it's really just where the inside of this radical is equal to 0. So you're going to get t squared equal to 4, which gives you t equal to plus or minus 2, doing the square root on both sides. So your important values here. So disappointed with this problem. Rt equals square root 2, t equals negative square root 2, t equals 2, and t equals negative 2. For your critical values, looking at this original function, the domain issues you're going to have are really just the inside of the radical. The inside of the radical needs to be greater than or equal to 0. I really didn't want this problem to be this bad. This is really frustrating. I just wanted one where you could practice, not where you would do a bunch of algebra. All right. Well, anyway, this is because the reason I'm a little frustrated here is because this is going to end up being a sign chart just to find the domain. And I didn't want that. So if you found these, let's just call those important values good enough for now. I really apologize that those problems didn't work out nearly the way I wanted to. Serves me right for grabbing them randomly from a textbook. Let me give you a new page here. I'm going to go find from a different resource, find practice problems, because I really do think you need some practice with these, but I want them to actually work out. So let's look up critical value examples. Okay, let's give you this example. Try this one out. F of z is equal to 2z to the fourth minus 16z cubed plus 20z squared minus 7. Here's what I'm going to do. I'm going to silently work through this problem on the screen. I'm going to have you guys work through it. Try to not look up at the screen, but I'm going to go through this problem up here, finding the critical values and important values while you are working, but I'll do it silently so that you can kind of look up only when you need the help. So start working through this. Oh, so I had it up here. I was giving you guys a chance to work through it. But yes, it was positive all along. Somebody mentioned it wrong, and I did factor it wrong. Look, it was positive. You can tell. Oh, goodness. Well, you at least got the right answer. So, yes, it should be z minus 1, z minus 5, and then just remember to get that z equals 0 from the front. And because there's no domain issues here, all those important values are going to be critical values. Which was what I was hoping was going to happen with this other problem we had down here that it didn't work out with. All right. So, any questions on that one example that actually went well and not the examples that didn't go well? For this one, I would say the important thing here is practicing algebra because the algebra is important. And, you know, maybe you got these values. That would be really nice too. But other than that, the ones I had you try down here were not as important as the one I had you try on the other page. Did the one over here go okay? Minus the part where I didn't factor it correctly. Okay, excellent. Excellent. Okay. Let's do this example. This example will actually work out. So, finding the critical values of this function. Here's the thing I want to mention about this. This is square root 3 theta. So theta is not under the square root. That's important here because that would give us some domain restrictions. But cosine doesn't have domain restrictions, and theta, as long as it's not under that square root, won't have domain restrictions. So there's no domain issues, which means all of your important values are going to be critical values. So we want to take the derivative, and we want to set it equal to 0, and find out where it doesn't exist, if that's a thing. And also important here is that we are given an interval. It's an open interval, but we're given an interval. So any answers we find should just be within that interval. Oops, let's find the derivative. The derivative, for this guy, it's just going to be square root 3 because the theta would disappear. It would be like it was 3 theta. Taking that derivative would just be 3. If it's square root 3 theta, derivative of that would be just square root 3. So we have square root 3. Derivative of cosine is negative sine, so this will be minus 2 sine theta. And we're setting it equal to 0 to begin with. This is going to require you to think back to some trigonometry. You're going to get square root 3 equals 2 sine theta. Dividing both sides by 2, you get square root 3 over 2 is equal to sine theta. This requires thinking back to your unit circle. There are going to be 2 places on the unit circle where sine theta is equal to root 3 over 2. This is asking you at what theta values and has to be, again, on this interval between 0 and 2 pi. Is sine of theta equal to root 3 over 2? So sine, if you remember, refers to the y values. So if the sine value is positive, that means that you're looking at quadrants 1 and 2. That's this quadrant 1, quadrant 2. The first place that theta is equal, or that sine theta is equal to root 3 over 2 is going to be at pi over 3. So at pi over 3, you have 1/2 comma root 3 over 2. So the sine value, the y value, is root 3 over 2. The other time that happens is going to be at 2 pi over 3. For this guy, you have the coordinate point negative 1/2 root 3 over 2. So this happens at theta equals pi over 3 and 2 pi over 3. Those are the two times between 0 and 2 pi that sine theta is equal to root 3 over 2. Once again, I don't want to go too much into the trigonometry of this because technically you took the trigonometry, so it should be somewhere in there. But remembering your unit circle is important here. So these are the values where the derivative is 0. Where does the derivative not exist? Well, this thing right here, there's no issues, right? Sine is defined everywhere. So there's not going to be any, him. There's not going to be any places where the derivative doesn't exist. There's no denominator to look out for. There's no radicals. There's no logarithms. And sine is defined everywhere. So we don't have this issue anywhere. So our important values are just going to be theta equal to pi over 3 and 2 pi over 3. And our critical values are going to be the same ones because there's no domain issues here. So once again, let me kind of go back. Recapping. For finding critical values and important values, you're really finding those important values first, and you're taking the derivative, set it equal to 0, and find out where it's equal to 0 or where the derivative doesn't exist. Those are your important values. Then, to limit down the critical values, you just look and see if any of the important values have issues in the original function. So remembering back to this example where the derivative was given to us, here you had 4 important values, but the 2 important values here, negative 2 and 4, that we got are not critical values because they made the original function undefined. So critical values have to be defined in the original function. But important values don't have to be defined in the original function. All right, so here's a theorem that is going to sound a little bit mathy, but I'm going to show you a picture of it, and you're going to say, oh, well, that does appear pretty obvious. So if f is continuous on the closed interval a to b, then f attains both an absolute maximum and minimum. And further, those absolute extrema will occur either at an endpoint or at a critical value within that closed interval. Very mathy way. This is the extreme value theorem. That's a very mathy way of saying something that's more or less obvious. Once you see the picture. Let's look at the picture though. So the thing is, we're on a closed interval. So here's A, here's B, and the function has to be continuous on this interval. So if I draw whatever function I want to draw, Oops, let's see. And it does not matter what we do here. I might want to make this a little bit less steep here so I can prove a point. Then it's saying that an absolute max has to occur, an absolute min and max have to occur. If you're continuous from A to B and you include your endpoints, then there is a highest value and a lowest value. Y value, that is. It has to happen. And that makes sense, right? There's no way for you to not, if it's continuous and it starts here and it stops here, there's no way to not have a highest value and a lowest Y value. The second part of this says, hey, this is either going to occur at an endpoint, so these are endpoints, or it's going to occur within the interval at a critical value. Which makes sense, right? You have critical values. So the critical values are where your extrema can occur, right? If we look back at this, this little beautiful picture here, critical values are where your extrema appear, right? So all extrema happen at critical values. So the possible absolute maxes or mins happen at one of these locations. That would make sense, right? Where the derivative is equal to 0, so the tangent line is horizontal, or at a point where it's at the end of the interval. The continuity part is really important here, and so is the closed interval part. But the continuity part is really important because if you didn't have continuity, then you could have asymptotes. Right? And this guy wouldn't obtain an absolute max or min because he doesn't have continuity in him and he has these asymptotes, and so there's no absolute max or min. But as long as you are continuous, so you don't break up at an asymptote, and you have these closed endpoints, one of these values is the biggest, is the highest y value, and one of these y values will be the lowest y value. There's no way for it to be impossible to find. That's what the extreme value theorem says. As long as you're continuous on a closed interval, you'll be able to find a highest y value and a lowest y value. Sometimes there's ties that can happen, but you know you'll be able to at least find one that is the highest. It might be tied with another, but they at least exist. It's not like this picture where it's like you can't find an x value that has the lowest y value. So here's how we use the extreme value theorem. We find the derivative. We find the critical points, the critical values. And we set, so we find the critical values, which is the process we've practiced. Then what we're going to do, so by finding the critical values, in this picture right here, we would find this value, this value, this value. We'd find these x values. Then you take all of the x values where there are critical values and the x values of the endpoints, and you plug them back into the original function to find their y values, and then you pick out the biggest and the smallest. So let's see it in action. Here we have an interval, f of x equals x cubed minus 3x squared, and we want to find the absolute extrema. So step-by-step process. Step 1. We want to find the derivative. Find f prime of x. That's going to give us 3x squared minus 6x. Step 2. We want to find the critical values, and there's an important extra part to this. We want to find the critical values that are in the interval that we're given. So we were given the interval -2 to 1. We only care about the critical values that are in that interval. If we are finding absolute extrema, right? If we're finding absolute extrema on a closed interval, all we care about are the critical values in this interval. So we're taking our derivative, we're setting it equal to 0, factoring out a 3x. So we have x minus 2 left over. We get x equal to 0 and x equal to 2. These would be our critical values. And they're critical values, they're important values and also critical values because there's no domain issues in this original function. But in the interval -2 to 1, 0 is in that interval, but 2 is not. So we're going to discount him and not use him because 2 isn't in the interval -2 to 1. Then we take the critical values and the endpoints and we plug them back into the original function. So the original function is this guy up here. So we find f of 0, that's our critical value. So 0 cubed minus 3 times 0 squared, that's 0. And then our endpoints are -2 and 1. So we're plugging -2 in. -2 cubed minus 3 times -2 squared. So -8 minus 12, that's -20. The other endpoint is 1. 1 cubed minus 3 times 1 squared. So 1 minus 3 is -2. From here, it's this part's the nice part. You're just finding the smallest one and the biggest one. And once again, this is when you're finding absolute extrema. You're finding the critical values, taking the endpoints and the critical values in your interval, plug them into the original function, and then pick out the biggest and pick out the smallest. For us, the smallest value we have is -20. That's going to be our absolute min. The biggest value we have is 0. So that's going to be our absolute max. So our absolute max is at, and we're going to put the coordinate point here. So the x value is 0, the y value is 0. We have an absolute max at 0, 0. Our absolute min is at, the x value is -2 and the y value was -20. So once again, for the absolute extrema, you have to compare the values. So on a closed interval, you're comparing the values in the original function of plugging the x values into, so the x values of the endpoints into the original function and the x values of the critical values, or rather just the critical values in general that are in that interval into the original function. Once you've done the setup work, doing the rest of the work for a different interval isn't as bad. So if we're talking about this same function and we want to go over the interval 1, 5, We've already found the potential critical values, right? The critical values are 0 and 2. If we're looking at the interval 1 to 5, we won't look at 0 because 0 is not in the interval, but 2 is. Then we're taking our endpoints and our critical values and plugging them into the original function. So why don't I go ahead and do my critical value first? F of 2, so that's 2 cubed minus 3 times 2 squared. So 8 minus 12, that's negative 4. And then my endpoints. So 1 cubed minus 3 times 1 squared. 1 minus 3, that's negative 2. And then f of 5, 5 cubed minus 3 times 5 squared. So that's 125 minus 75, which is 50. Then you're taking the smallest value, and that's going to be your absolute min. And your biggest value will be your absolute max. So the smallest value is negative 4. That's a y value, right? The smallest y value is negative 4. So it's an absolute min. The biggest value is 50. So that's the absolute max. So the absolute min is at the coordinate point 2, negative 4, and the absolute max is at the coordinate point 5, 50. Can I answer any questions on that? I'm going to find one for you to practice, and I'm going to double check to make sure all the things work out nicely. Now, sometimes the numbers won't come out to be nice. Sometimes you'll have to just plug them in your calculator. Other times the numbers are nice ones. But okay, let me give you one. I know this one works out, so I'm going to give you one to try for finding the absolute. The absolute extrema. So try this guy. R of t equals 1 plus 80t cubed plus 5t to the 4th minus 2t to the 5th, and we're on the interval 0 to 7. Actually, I'm going to change my mind and make it, negative 1 to 7. Right. So follow the process. I'm going to give you 3 minutes, right? 3 minutes to find those critical values, and not critical, to find the absolute extrema. All right, I remembered to click record this time. Okay, so let's see how this has gone. Nice thing is this is a polynomial, right? So we're good in good shape to start off with. So we're going to take the derivative. I'm going to get 240 t squared plus 20t cubed minus 10t to the fourth. We're setting this equal to 0. I'm going to factor out as much as I can. I can factor out a 10, and I can factor out a t squared. So if I factor out a 10, I get 24. The t squared got factored out. And I'm sorry for that clicking in the background. My dog is in a cone. Toby, come here. Let me itch your neck for you. Come here. I can't help you if you're going to sit over there. My dog's in a cone and his neck is itching, and he's itching his cone instead of the neck, so I apologize for that noise. Poor guy. But he's not going to come over to let me help him. Of course. Plus 2t minus t squared equals 0. Rewriting this so it's in descending order, we have negative t squared plus 2t plus 24. I'm going to go ahead and factor out a negative as well so that we can factor this one nicely. So negative 10 t squared minus 2t minus 24 equals 0. This will factor rather nicely. So we have t minus 6 times t plus 4 equal to 0. If you set negative 10t squared equal to 0, you're going to get t equal to 0. This gives you t equal to 6, and this will give you t equal to negative 4. Now, we're in the interval negative 1 to 7. So negative 4 doesn't fit in that interval, but the other two do. So we have to check 4 different points. We're going to need to check 0, 6, negative 1, and 7. And we're plugging them back into the original function. So r of 0, that'll be 1 plus 80 times 0 cubed, plus 5 times 0 to the fourth, minus 2 times 0 to the fifth, and that's just going to be 1. r of 6, 1 plus 80 times 6 cubed, plus 5 times 6 to the fourth, minus 2 times 6 to the fifth equals, I don't know, use your calculator. That's not something I would suggest doing by hand. I got 8209. If you get any different numbers for the ones I'm getting, let me know, because I'm just kind of quickly plugging them in. So those are our critical values in the interval. For our next two values, we're going to be plugging in the endpoints, so negative 1 and 7. So 1 plus 80 times negative 1 cubed, plus 5 times negative 1 to the fourth, minus 2 times negative 1 to the fifth, equals, let's see, 1 minus 80 plus 5 plus 2, negative 72. And for 7, plugging it into my calculator, I'm getting 5832. Did anyone get different numbers from that? All right, that's always good. So then you pick out the smallest and the biggest. The smallest guy right down here. So this will be our absolute min. Our biggest one right here. Absolute max. So there's an absolute min at the point -1, -72, and there's an absolute max at the point 6, 8,209. It can be a bit tedious, especially with the plugging in, but the process isn't that bad. It's really important that you remember how to factor. Factoring is never going to go away. Factoring is never going to be not a thing. For the rest of math, factoring is going to be important. So if the factoring is something, if this part up here was getting you down, that is definitely something you want to practice. And I do have those resources available on my on the resource page. If you go to Canvas and then click on resources, there's factoring practice. If you, at this point, are feeling a little bit uneasy about your factoring. Can I answer any questions on that example? All right. So then, let's try this one. Now, I think I'm actually going to let you try this one. I think you guys can do this one. Some things I'm going to mention before you start trying it is that this function right here, it has no domain issues, so all important values are critical values. The other thing I'm going to mention is that e raised to the I don't care will never equal 0. This is going to come important when you go to do some parts of this problem. So e raised to the x squared, e raised to the x, e raised to the I don't care what you have up there, it's never going to equal 0. So that's something to keep in mind. So with that being said, I'm going to go ahead and give you, I'm going to give you 4 minutes. I'm going to give you 4 minutes to do this problem. Try this one out. I think you guys can do this. I think it's going to be okay. All right. So let's go ahead and look at this one. So first of all, we will be doing product rule and chain rule here. So let's see, this is g prime of x. So f prime is 1. G is e to the -2x squared. So f prime g plus g prime. So the derivative of e to the -2x squared will be -4x e to the -2x squared. That's g prime, and then times f is x. Let's simplify a little bit. And then the key here is that both of these terms have an e to the -2x squared in common, and we can factor those out. So e to the -2x squared, we have 1 minus 4x squared. And we can set this equal to 0. 1 minus 4x squared can be factored into 1 plus 2x times 1 minus 2x. Then this part, the e part, that will never equal 0, so we don't have to worry. This factor gives me x equals -1/2. This will give me x equals +1/2. Now, we're on the interval 0 to 1, so we don't care about the -1/2. I only care about the 1/2. I'm now going to plug in 1/2 and 0 and 1 into my original equation to look for absolute maxes and mins. So we'll do g of 1/2 first. That's 1/2 e to the -2 times 1/2 squared. So this is going to simplify to 1/2 e to the -1/2. And if you plug that in your calculator, that's going to be approximately 0.303. Plugging in the endpoints, we have g of 0. That'll be 0 times e to the negative 2 times 0 squared. It's not going to matter. 0 times anything will be 0. So that's 0. And then g of 1. So that'll be 1 times e raised to the negative 2 times 1 squared. So that's e to the negative 2, which is approximately 0.135. So the biggest value is this guy right here. So this will be our absolute max. Our smallest value is 0, so that's going to be our absolute min. So we have an absolute max at 1/2 comma, and now we're going to give an exact value because we only rounded here to see where those values were. So we needed to, I can't look at 1/2 e to the negative 1/2 and tell you if it's bigger or smaller than e to the negative 2. I just can't look at those numbers and tell off the top of my head. So we plug them in to figure out where they fit relatively. But the answer we're going to give is the exact answer. So I'm going to do 1/2 comma 1/2 e to the negative 1/2. And our absolute min is at the point 0, 0. How did that one go? Was that one okay? Excellent. I'll take went better than I thought. I'll take that for sure. Okay. All right. So for our last problem, we're going to do a word problem. These ones are near and dear to my heart because when I taught at Ohio State, I taught a lot of business calculus. And you may have remembered from a few lectures ago me complaining about variables that get used. And I told you guys that I hate the letter Q as a variable. I don't feel like Q should be a variable. And it was because of teaching too much business calculus. So near and dear to my heart are these business problems. So let's talk business for a tiny bit. The revenue of a given computer can be approximated by the function r of q equals negative q cubed plus 15 halves q squared plus 450q, where r is measured in thousands of dollars and q is measured in hundreds of computers. If the company can produce at most 2,500 computers, at what quantity will they reach their absolute maximum revenue? So they're giving you information without telling you that you're giving you information. So Q is measured in hundreds of computers. And the company can produce at most 2,500 computers. So they're giving you an interval without telling you they are. Because what's the minimum number of computers that a company can produce? I will take answers. What is the minimum number of computers that a company could produce? 0, right? They could choose to just not. They could choose to not produce. So 0. And then it says the most they can produce is 2,500. Now, because Q is measured in hundreds, we can say 25 here. So we have this closed interval, 0 to 25. They didn't tell us, but they did tell us. And now we can do the process that we've done before. So find r prime of Q. And here's our r function here. So that's negative 3 Q squared plus 15Q plus 450. We'll set that equal to 0. We can factor a negative 3 out. So you have q squared minus 5q minus 150 equal to 0. This will factor into q minus 10 minus 15, q minus 15, times q plus 10. Giving us q equal to 15 and q equal to negative 10. Now, our interval is from 0 to 25, and clearly it doesn't make sense to produce negative computers. You don't just go and steal computers. That's not how companies work. So that's not in our interval. And we will not worry about it. And now we have endpoints to try, and we have q equals 15 to try. So r of 15 will be negative 15 cubed plus 15 halves times 15 squared plus 450 times 15, which should come out to be 5,062.5 if you plugged it into your calculator. Plugging in our endpoints, 0, as you can hope, plugging in 0 gives you a revenue of 0. So if you make no computers, you make no revenue. That would make sense. And then plugging in the most computers, they can make 25. So this is negative 25 cubed plus 15 halves times 25 squared plus 450 times 25. And this should give you 312.5. So we're not asked about absolute max and absolute min here. Instead, we are asked what quantity will they reach their absolute maximum revenue. So we're looking for the highest revenue. This is the absolute maximum revenue. And that happens at 1,500 computers. That's important here because Q is measured in hundreds. So the absolute max is at 1,500 computers. And 1,500 computers would be 1,500. Computers. And the revenue they'd make. Now, I do think this problem was meant to say that the revenue, not because the way it reads is that the revenue per computer would be this much. I don't believe that's what this was trying to say. I believe that this problem was trying to say that the revenue in general would be 5,000. I don't think that the revenue they're making per computer was 5,000. Otherwise, sign me up for that tech company. But anyways, that is all for this section. Oh, they actually added some on here. That's okay. We'll come back and do that one. We'll come back and do that one on Wednesday. So that is all I have for you. So remember, exam 2 is posted. I will be posting practice problems for section unit 3 soon. They're not included in the notes, but I'll be posting them soon. And if you have questions or concerns, feel free to email me. Otherwise, I will see you guys all on Wednesday. I'll stick around for any questions. Otherwise, have a nice week. Bye.